Hello, Physics 1 students. Um, this is a video, it's kind of a little bit of a side topic, I suppose. Think of this as a problem-solving help, kind of a vocabulary help for solving physics problems. And in many problems, we are told that there are no slipping conditions. So what I want to do is kind of unpack what those imply, especially when we start to think about objects that are rolling with no slipping. Um, so uh, let's just dive into it. So there are various types of situations where we have objects that rotate. So you might have a circle that rotates and kind of moves forward. Okay, and there's a center there. Center of mass is in the middle, let's say. And there are various quantities that you might want to relate. We have a change in theta, right? So if you imagine it starts at some angle theta, and then, so we mark a line on the wheel, let's say, and then later on, that line has rotated down through an angle theta. We have omega, the angular velocity, we have alpha possibly, and then we have various quantities around the edge of the disk. So like, for example, you could have an arc length. That would be the distance along the rim here. Call that something like delta S. And then you could have a tangential velocity. So that would be the velocity, say, of a marked point on the edge of the wheel. And you could talk about a tangential velocity. You need to say relative to what? So in this case, I could be talking about relative, say, to the center of the wheel. We could also have an acceleration of that tangential point relative to the center of the wheel. And then you could also have a centripetal or radial acceleration. And then we also have, so that's all about the kind of the motion or the linear quantities relative to the central point. But then we can embed this spinning wheel in the ambient space, along the table. So that can turn into a statement about what is delta x for the center of mass, the central point. What is the velocity of the center of mass? What is the acceleration of the center of mass? So in general, the relationship can be a little complicated between all these things. However, when we impose no slipping conditions, that really tightens things up, and there aren't quite as many kinematic variables as you might imagine. All right, so that's really what I want to sort of address, kind of work through the details of what a no slipping condition will buy you in a problem, and and that kind of then becomes sort of a secret code word. So when you read no slipping in a problem, there's a whole list of assumptions you're allowed to make, and if you don't make those assumptions, you're probably not going to be able to solve the problem. Let's proceed. First thing I want to do is kind of show you a video of me rolling a plate across my kitchen table, or kitchen counter. And what I have, let's go back to the beginning, sorry. We're going to roll this. I've done it in slow motion. I want you to follow the motions of the different points on the plate. It's kind of interesting. So you'll notice that the central point just moves horizontally. The moment of, or the motion of the contact point is kind of complicated if you look at it. Let's see if I can draw. I'm not sure I can draw on this or not, so we'll see. We'll see if it lets me do it. I'm going to mark this point right here. And we'll start the movie. And then let it move a little bit in time. Sorry, I'm struggling with the stylus. Hopefully that works. All right, so I'm just kind of going to fill this in. Sorry, it's taking so long. Stylus just isn't very easy. I have too many menus to switch between to make this work. One more. We'll do one more point. So one thing to note. Oh shoot. There you go. All right, you get the idea. I'll just leave it there. So we watched the movie. Look at the kind of funny motion of the point on the rim of the plate. It really has kind of an interesting path. Let's try another idea. So it kind of goes down, makes contact. And then follows this kind of an arc. So it kind of makes this sort of V shape as it goes down and hits the table. So that's kind of an interesting thing. Whereas the point, the center of the wheel just follows a horizontal line. So the different points on the wheel go through different sorts of paths as it rolls without slipping. Okay, let's go back to the whiteboard space. Okay, so if I have a wheel that rolls without slipping, So let's imagine I've got this wheel. I'm going to collect some facts that we sort of know. One thing you could do is imagine that there's a string which wraps around the outer edge of the wheel. Okay, and you could imagine that as you kind of unwind that string, so as the wheel rotates, you sort of can imagine you leave the string behind. So what we could say is at the beginning, we have this point here on the edge, and then directly above it is the center of the wheel. And then as you unwind, as you roll the wheel without slipping, that string would be left like a trail behind it. And then we would end up with the wheel shifted over. And if you make one full turn, if you think about it, you're going to have that initial contact point back here at the bottom, and right above it is, again, the central point. So you can ask, okay, well, how far? So the red and blue dots start out lined up. You go through one full cycle, and they're now lined up again. You could ask, how far have they moved horizontally? And what we see is that delta, the distance traveled by the center of the wheel, of the center, is the same as the distance around the wheel. So we find that delta x is of the center is going to be nothing other than 2 pi r, the circumference of the circle. That's kind of an interesting fact. The other thing I wanted to point out was if you follow the motion of the point, the red dot, as the wheel turns, you'll see that as it makes contact with the surface, it kind of goes through this sort of pattern. Makes contact, and then as the wheel continues to turn, it pops up and makes that kind of pattern. And it actually follows, if you had multiple turns, it would look like this over and over and over. So these are what I was trying to show in the video. So this is what the red point would do, whereas the blue point would simply just move horizontally. So it would be, just follow a horizontal flat line. It doesn't move up or down. That's kind of interesting. What this tells you, you'll notice that at the point of contact, there's no relative motion. The velocity along the ground is actually zero relative to the velocity relative to the surface is zero at the contact point. Now, it actually has a tangential velocity. So relative to the center of the wheel, the contact point is moving, but relative to the table, it is not. So one of the things that means is that because there's no slipping here, that means that the only kind of, so we can think about what kinds of forces could be at play at the contact point. And at the contact point, we can pretty much only have a normal force, which would point upwards, and static friction. We don't even know if it's maximum, if it's the maximum static friction. We just know that those are the two that are allowed. If it was slipping, you would have to handle kinetic friction as well, and also possibly look at the transition between them. For those of you going on to studying engineering, that's the kind of problem you would study in dynamics. You push a block and you'd figure out, okay, at what point, how should you push it, and at what point on what place along the object so that it slides, or so that it slides, or that it tips, or that it slides and tips, and any of the different kind of problems like that. Okay, so those are kind of different things I wanted to highlight. People think because it's moving that actually the contact point is moving relative to the table, even though, because the wheel is moving relative to the table. But that's not true. The contact point actually has no relative velocity to the table, even though the center of the wheel continues moving steadily. All right, so there's that. Well, okay, so let's kind of go back then. We've seen some relationships between angular quantities and the points on the rim of a spinning object. Now we want to kind of connect that to motion along a table. So again, I'll draw my picture here. I have a wheel. We're going to imagine there's an angle that changes. We're going to imagine there's an arc length along the edge of the wheel. And then we're going to imagine that there is a horizontal displacement, delta x. And that's the displacement of the center of the wheel. So we talked about, when you had an object that rotates, that there's a relationship between the change in the angle and the arc length, or the distance traveled by a point along the wheel. And what we found was that r times theta equals the arc length, and I'm being a little cavalier with minus signs. I'm not going to worry about minus signs, basically. Well, not yet. I'll come back to minus signs when I need to. But this angle, the way I've drawn it, should actually be a negative angle because it is a clockwise rotation. Okay. On the other hand, what I just try to show is that if you make a full turn, the horizontal distance equals 2 pi r, and if you made a half turn, it'll only be pi times r. And if you made any sort of fraction of a turn, it actually has the same formula. So up to a minus sign. So what we find is that the motion, the horizontal motion, when you roll without slipping, of the center of the wheel is actually the same as the arc length traveled or kind of rotated through. And that gives us a relationship between angular quantities, tangential quantities, and kind of motional quantities along the table. Right? There's a little, the actual relationship though does have a minus sign, because a forward motion in the horizontal direction corresponds to a negative rotation. So I would actually say that delta x is minus r times theta. I guess it should be delta theta if I'm putting in the minus signs. That's fine. We can take derivatives of these things because these relationships are true over an extended time period, but they're also true kind of instantaneously because the radius doesn't change as a function of time. So what we actually get is then r times omega. That's like, or that up to a minus sign is v tangent. If we're talking about magnitudes, then they're equal. And then that's going to be, well, in the same amount of time, you go through the same distance around a point on the rim will travel the same distance around the center of the wheel. So that's measures v tangent. But in that same amount of time, it travels, the center of the wheel travels the same horizontal distance. So actually that must equal the velocity of the center of the wheel. And again, if we're being really careful, we should say that velocity of the center equals minus r omega, just because when I have a clockwise rotation, that's a negative omega, but that corresponds to a positive velocity. And I can take one more derivative and I find r times alpha is equal to a tangent. And that should then be associated, no surprise, with the acceleration of the center of the wheel along the ground. And again, I have the same minus sign issue. Okay, so because of the no slipping condition, we're able to correlate the change in angle with a motion along the table. If you start to slip, it's more complicated than that, and you have to work harder. Okay. The next scenario I want to discuss will happen when we have like a pulley, or I don't know, some sort of rigid object that can rotate. And we're going to imagine that we have a rope which is wound around it, say, many, many times. And we're going to assume that the rope is not able to slip. So again, it's a no slipping condition. It's going to allow us to make some of these statements. So we're going to imagine this is a fixed wheel that spins, a fixed pulley that spins, and the rope is going to go up and down. Now, on the rope, you could imagine, let's say there's a mass or something like that. And in this problem, we're not trying to compare horizontal distances to angular changes. What we don't want to do is relate angular changes to things like, you know, the change in the height of the mass. But the idea is very similar. Again, if this wheel makes one full turn, then that spools out a length of string equal to 2 pi r, and that then relates to the change in the height. And in this case, we notice that if the spool is, or if the string, or if the wheel is turning clockwise, so it's a negative change in angle, that corresponds to lowering this mass. And so you'd actually have the same minus signs between the kinematic quantities describing the mass and the kinematic quantities describing the rotation. So we would find in this problem that r times theta equals, delta theta equals delta y, so that if you have a positive change in theta, then you're raising the height. That makes sense. Counterclockwise rotations raise the mass. If you had a clockwise rotation, you get a lowering of the mass. And similarly, then we would say r omega equals the velocity of the mass, and r alpha is going to equal the acceleration of the mass. So that one's pretty easy. Let me just point out a possible, you have to be careful when you draw these things. Let's imagine that I have the same pulley and I wound it the other way. Again, I wind it up with no slipping. And then I have the same mass sitting there. You know, it's pretty much the same problem. And conceptually, it is the same issue, same relationship. However, there are minus sign things happening. In this case, if you lower y, that actually corresponds to a positive angular change. And if you raise the mass, that corresponds to a negative rotation. So what we find in this case, because we've wound it the opposite way, is that r delta theta equals minus delta y, and that r omega equals minus the velocity, and r times alpha equals minus the acceleration. So watch your minus signs. Think about what's happening. It's just a tiny thing, but the minus signs matter when you start doing algebra. Okay, so the minus signs matter, and you'll get bizarre answers if you start dropping those. Okay, so that's a little video. Hopefully that spells out some of the common assumptions that can be made when you have something that rotates or some sort of no slipping condition. Um, and we will use these in different problems.